Good morning, everyone. My name is 𝗦𝗧𝗕𝗦𝗬𝗧. Thank you very much for attending. Just gonna have the camera on at the beginning and at the end, just so I don't want to distract myself too much. Thank you very much for attending, and for the last episode of this series of webinars this year, episode 10. Can't wait for dead time compensators. A few guidelines before we start. Your microphones are off. So therefore, if you need to ask questions, there will be a Q&A at the end. You can type in your question anytime you want through the Q&A box, and I will read out your questions and answer them as well. And so therefore, now there is a 10-second time delay from the moment I speak to the moment you hear my voice. So if light travels at 300,000 kilometers a second, that means I am 3 million kilometers away from you. I'm actually broadcasting here from the spaceship Discovery on my way to Jupiter to investigate some crazy monoliths that are orbiting Jupiter right now. Your questions are anonymous, so only I can see. So there's no bad question, and I really encourage you to ask questions. And like I said, don't be embarrassed, don't be shy. And if we do not have time, or if you think of a question afterwards that maybe oh shuck, I should have actually asked them that question, you can always reach out to me at 𝗦𝗦𝗕𝗦𝗧𝗔𝗬@lakesidecontrols.com, and my probably cell phone is the best way to get a hold of me. And like I said, this is a series of lunch and learns. So this is the very last one. Can't wait for dead time compensators. I do plan on having webinars next year. I'm just trying to decide on a few subjects and possibly kind of a bit of a rehash of previous webinars with some real live case studies. If you have any ideas of what you would like to have covered, please reach out to me. I certainly would appreciate that. Now, this is being recorded, and at the end of the webinar, you will receive a link. And so if you want to go back and listen to the webinar again, that'd be fine. All my webinars have actually been recorded. So if you want previous recorded webinars, just reach out to me as well, and we'll arrange a video link as well. Just a word of caution: some of them I've actually pressed record a little too early, and so as you kind of view them, you'll need there's probably quite a bit of dead air. You need to fast forward, which is always a good thing. Safety moment. Obviously, we're nearing the winter solstice, getting dark very early, and driving in the dark is actually obviously very, very hazardous. Accidents rates do increase while we drive at night. Obviously, try to limit your driving at night. I know right now, actually, I kind of try to go to the grocery store probably during the day at lunchtime if I can. That way I can avoid driving at night. Obviously, don't overdrive your headlights. If you are, another kind of personal factor here, actually, I walk my dog every night in our neighborhood. We're in this kind of a generic subdivision, and there are cars parked in the driveway. Sometimes you see a car running, you're walking by, and as they back up, they don't always check if there's someone walking in the back. So what I do, actually, I wear my high-vis winter jacket, and it's made a big difference. So again, so let's be careful going through winter solstice. The good news is that past December 20th, the days will be getting longer. Yay! A little bit about Lakeside. We can trace our roots back in 1952. It says 325 employees. I think now we've been on a hiring spree. We're actually near probably 350 some odd employees. We have offices obviously right in Mississauga. We just got a new facility in Dundas, Ontario. We'll be doing a lot of our manufacturing and assembly there, which will replace our facilities in Guelph. We have offices in Port Elgin, Sarnia, Sudbury, Thunder Bay, and Winnipeg. And so we've actually, although we work in many, many industries, we're part of what we call the Emerson Impact Network. There are 21 of them, and we all have a set territory. So you can see we're number 9. Our territory just goes just from this side of the Kingston border to the Manitoba Saskatchewan border. And out west we have Spartan controls, and out east you have Laurentide controls. And why Emerson Impact partner like this? Why does Emerson want to partner up with local people? Because we actually think you get better service, better contact when you actually when you actually have a local presence as opposed to a large monolithic corporate presence. And so obviously one point of contact, you present us with some of your challenges and we have solutions. If we're not sure, we know who to talk to at Emerson to actually get the proper solution for you. And we do sell a lot of stuff, obviously instrumentation, the standard for pressure, temperature, level, flow, analytical. We also have on the actuation side, we have control valves, isolation, pressure relief, regulators, and so forth. Control system, we got mainly Delta V, though we do work with Ovation system as well. And obviously, there's a lot of other things there. This is a very busy slide, not my most favorite. And we do also consulting services, life cycle services, and educational services as well. And we're here to provide you with a positive customer experience. And I think at the bottom of our email we have any kind of email signature. You can click on there and provide us with feedback. And I always say there's no such thing as bad feedback. All feedback is good feedback for us, and we do take it seriously, and we do make sure that we try to improve upon your customer experience. A little bit about myself. I actually have over 30 years experience, and we have two other gentlemen that kind of help me out once in a while, Andrew Boyton and Dean. I might have another mini me coming up pretty soon. I know he's attending right now. Hopefully I'll be able to bring him in the fold. Some of the services: control loop optimization services, loop tuning assessment. I was just up in Sudbury last week tuning a pH controller. So I do go to site, and I do some work remotely as well, obviously with this pandemic. Also do work on alarm remediation. If anybody you actually have the, look at your control panel, your DCS screen, your alarm screen. There's a good chance that it's full of alarms. A lot of them are probably nuisance alarms. We say that 80% of your alarms are due to probably eight sources or less, or 10 sources or less. And so we're there to actually analyze your alarm, the occurrences of the alarms, and determine which ones are nuisance alarms, make recommendations. And the whole idea is not to eliminate alarms, but to make alarms relevant. And that's not a stock picture there. That's an actual picture we took at here that we took at customer site, where this alarm kept going off and someone decided to stick a steak knife in there. And I do teach courses as well. I teach a basic instrumentation course. It's about a 6-hour course. I will be coming up with my training schedule for the first half next year. So pay attention to our website. I teach also process control techniques 1, aka loop tuning, where we talk about different methods of loop tuning out there. And there's also loop tuning 2, process control techniques 2, where we kind of take it a little bit further. We talk about gain scheduling and some of the things that we actually talked about during these webinars: feed forward control and gain scheduling and so forth. I do have a blog as well, so kind of accumulation of some of the experiences I've had through my 30+ years experience. I try to make them kind of a bit humorous, but they not super technical, trying to make them fun to read, but there is always a bit of a moral to the story at the end. So you just go to our website, lakesidecontrols.com, just search for Confessions of a Looney Tuner, or just blog and it should pop up. All right, now here's the good stuff. Okay, we're going to talk about dead time compensators. Like, why do we want to use a dead time compensator? And then after that, we've got to start the why. Then actually, what is a dead time compensator? What does it do? The different types available out there, and then how to implement a dead time compensator, and then dynamic models. And we'll cover all these things throughout today. So why? What is dead time? Dead time is the time delay. Please don't call it lag. Lag is a time constant. It's one of my pet peeves, but if you do, that's okay. But it is time delay or dead time from the moment I make my bump to the moment I first start seeing a change in my process. And a typical PI or PID controller is a very, very impatient beast. When it makes an output change, it expects to see a change right away on the PV, not knowing, quote unquote, knowing that there's any kind of time delay. And so time delay is the single most destabilizing process parameter in the entire universe. Why do we have dead time? Well, some processes require dead time. So you think about here the pH. So we're adding caustic here, and obviously a chemical neutralization must occur before we can measure the pH. As a matter of fact, I encountered that last week where it was effluent pH I was trying to control. I did some bump tests. This is a bit of a side note. I did some step changes back in July when the water was warmer, and the reaction was was quote unquote normal. But what happened now is that we were measuring pH, but the temperature was, instead of being 21 degrees, was 1 degree Celsius. And that what I believe happens is the fact that as chemical reaction rate doubles every 10 degrees Celsius, so the reaction rate was actually so much slower that I was actually measuring residual sulfuric acid, which is what I was injecting. And so therefore my process was extremely sensitive. And so therefore the solution there would be to move the sensor further down to allow the sulfuric acid to react and therefore measure the proper pH. But I digress. Now, the other issue here also, when I say that the dead time should be kept to a minimum. And why is that? It's because I've seen a lot of times where we're going to install our pH over here somewhere. And even though we know that the chemical reaction will have occurred there, instead of having 20 seconds of time delay, we will now have 2 minutes and 20 seconds of time delay. Because, and I've seen this before, where actually they had to install a pH meter in another building because the other building was not an explosive atmosphere, and they didn't want to spend the extra money to buy a intrinsically safe pH meter and put it in the same building. And so obviously when we design our processes, it's important to understand, yes, some processes do require dead time, but to keep it to an absolute minimum. Why do we want to use dead time compensator? We want to use dead time compensator when the dead time to time constant ratio is greater than 3. That's what we call a dead time dominant process. So if you can see here, the top part here, where there's very little dead time and the same time constant, here I have the same time constant, but a lot more dead time. And so therefore, I'm going to require perhaps a dead time compensator. Not to say that a PI or a PID controller can't handle excessive amount of dead time, but we have to build so much robustness, aka detune it a little bit, that we may end up losing out on control opportunities. Now, there are different types of dead time compensators out there. Now, in Delta V, there's the MPC block. MPC stands for Model Predictive Control. And so this is actually, we have MPC, we have MPC Plus, and MPC Pro. So you can probably think that obviously it increases in complexity and capabilities. Now, the MPC block, the most common one, can handle up to, I believe, 8 inputs and 8 outputs. And so obviously there, it can compensate for the time delays in your process. So you can have a single input, single output, and it would be a dead time compensator. It could also incorporate disturbance variables. This is actually one that I developed here I was simulating a pasteurizer with different temperature zones. So actually here, disturbance variable coming in for my flow, and that can be used for feed forward controls. It also has constraint variables, so you can go above a certain variable or below a certain variable as well. So there's also dynamic matrix control, DMC. I think because Mr. Charles Cutler developed that in the 70s, if I'm not mistaken, for Shell distilleries, Shell oil. There's also the Dalene controller, which is used mainly in pulp and paper on paper machine controls. I'm sure there's a whole bunch of other ones as well out there. They all have kind of the sort of the similar theme, this common theme, and I'll talk about that in a minute. There's also the Smith predictor and the modified Smith predictor. And this is the modified Smith predictor is the one we're going to talk about today. I don't want to talk about MPC because you're not all Delta V users. So I want to talk about something that you can build within your own distributed control system. So how does this work here? So first of all, we got to understand the process. You've heard me say this before, thou shalt know thy process. And our process will have a process gain, a process dead time or time delay, and a time constant. And what we're going to do is that we're going to build a model, aka a simulation, aka a digital twin. That's what they call it these days. I don't know why. It's just a model, a high fidelity model, where we know we'd have to do bump tests, and we know the process gain, we know the dead timer process, we know our time constant, and therefore, obviously, this plus this is going to equal your process variable. So what we did here is that, and then what we're going to do is that we're going to measure the difference where our model prediction is and where our actual value is. The difference then will be either process disturbances or model mismatch. We'll talk about model mismatch later on. Now you have to understand here that the PID controller does not look at the actual process variable. What it does is that it actually looks at the model value and the differences coming between the model and the actual process. And so what we're doing is that we're controlling a model and we're injecting real life information about the process through that addition block. So essentially, the PID controller is working on that loop. And whatever it sends this way in terms of command output, it also sends that way. And once again, hopefully, if we have a good model, everyone here is going to meet up at the same time in the same way, and therefore will negate that model difference between the model and the process variable itself. So we did this because we wanted to separate the bad part. This is the bad part, the time delay. We wanted to actually put that on the other side. We don't want to deal with that. We're going to trick our controller and say, hey, there is no dead time. But then someone said, you know what? Not only don't I want time delay, I don't want to deal with that. I don't want to deal with the process time constant either. So what I'm going to do, I'm going to move that over this side, and that then becomes a modified Smith predictor. And what I'm then controlling, I'm controlling a P-only process. And of course, it's always difficult to write on a screen. A P-only process. So in this case, no matter, it's very difficult to tune a proportional only controller and have it overshoot and have it go unstable. So we're adding a bit more robustness to our proportion by using a proportional only process. Once again, though, I'm going to repeat myself redundantly, is that the controller still works off the model, and we're injecting real life disturbance process information via the addition block. So this is how I programmed it, and it's actually surprisingly simple to actually program this. So what I did here, the up part is actually, it's a simulated process, obviously. And what I did is that I went through a characterizer block. I could put a mild nonlinearity there if I wanted to. I didn't. I left it linear. So basically just a linear input. I put in 2 time constants of 2 seconds. So I made it second order just because, you know, it's just to make it a little bit funkier, a little bit different. There's my dead time block, and my process is at 15 seconds of dead time. That's the process dead time. This here is a block where I can actually add a bit of noise, a bit of offset. And if I want to, I can actually inject a low disturbance. All that gets added up, and this is my process right here, right there. Now for my Smith predictor, you can see I have my PID block right there, and it sends the output here, but it also sends it down to here. This is where I set my model, my simulation. I'm trying to simulate my process model. And if I do a good job, my process model will equal my process. And here's my model process gain, my model time constant. Note here that I've only made it a first order process, so there's already a little bit of model mismatch going on, and my model dead time. If you remember before, so this is going to be my model here, and I am subtracting the process from the model, and then I'm adding that to the actual proportion only part right here. I know there's a lot of stuff being written here. Let me just erase all that. And so what we're going to do is that part here will get sent over here as done programmatically. There you can't see a line, but they're actually connected. The PV then becomes input of the PID block right there. So what I'm going to do is I'm actually going to flip over and show you a live demonstration here. So here are the model dynamics that I have right now. So I have a model dynamic of process gain of 1, a time constant, model time constant of 3 seconds, and a model dead time of 15 seconds. And right now we're all pretty much bang on in terms of our model. There's actually very little model mismatch. You can see here I can add a low disturbance if I want to, and the case. So here, case 1 is PI control, and case 2 is your modified Smith predictor. So I'm going to take a look at this here. So what I have done here is that right now I'm in PI control mode. And the tuning is just regular tuning. Here I have a controller gain of 0.3 and an integral of 8 seconds. So right now I'm in PID mode. So what I'm going to do is that I'm going to change the set point here from 50 to 60%. And you'll see there's your output. So for those of you who are not familiar, the blue line is the output command out of the PID. The white line is the set point of the PID block, and the yellow is the actual process variable. And as you can see, the PID controller is reacting, and I tune it fairly conservatively so that I can actually, it will actually control. But it is obviously we have to compensate in our tuning practice, our tuning calculation. We have to compensate for the excessive amount of dead time, the 15-second dead time that we have here. And as you can see, it's reaching up, so it's actually pretty good. So the next thing I want to do is actually, this is kind of fun. I'm going to make the tuning more aggressive. So I'm going to make the tuning more aggressive. So I'm going to increase the gain from 0.3 to 0.6. I'm doubling the gain. I'm going to make the integral faster. For those of you not aware, the smaller the number in integral, if it's seconds per repeat or minutes per repeat, the more integral action I have. And I'll make that 3 seconds. So now I'm going to go back to my trend, and I'm going to make the same set point change back down from 60 to 50%. Now you can see there, obviously the higher gain, I got a lot more proportional kick, And you can see the integral taking over because the PV still hasn't changed. It's ramping down very, very quickly. And now suddenly the process starts to react. And I'm pretty sure you can see what's going to happen. And it's slowly going to go unstable. Now I'm going to let it go for a little bit here. And then after that, what I'm going to do is I'm going to switch over. As a matter of fact, this is really going unstable. So we'll just change the scaling here. There we go. So you can actually see it. It actually is going unstable. And obviously we tuned it way too fast because we have a dead time dominant process. So the next thing I'm going to do right now, I'll just complete almost, oh, there we go. Okay. So what I'm going to do now, I'm just going to change the controller mode from a PI controller to the modified Smith predictor. Let's see how that works. So you can see here a little bit of jagged responses when I switched over. And that's because there's some slight model mismatch. Again, I'm going to talk about that later on. Now, let's wait for a little bit here, but you can see obviously now the output is behaving a lot more stable. And you can see the PV will reach set point shortly. So that was when I first tried this. I was still kind of amazed how, just that one change made it very, very stable following the unstable part right here under PI controller. And what I'm going to do now is that I'm going to change the set point back from 50 to 60. And you'll see the controller essentially is working off the model, but now also with real life process disturbances injected into it. And you can see the PV coming up to set point. So I'm going to show this a little bit more during my slides, but I just want to just kind of pause here for a second and just let you see how it reacts. And you got to understand here that I've actually tuned it quite aggressively, very aggressively, but because of the model compensation, it's able to react properly. Okay. So this is where a bit of a comparison. There's the same gain of 0.3 and a reset of 8 seconds. And using slightly more aggressive tuning, modified Smith predictor, I'm able to reach set point. If I go back and forth, reach set point faster. And again, as I just showed you here, you can see here that little squiggly part here is when I switched it over from the PI controller to the model. There's a bit of model mismatch that can propagate through, but eventually it does stabilize. Now, one last thing I want to talk about is model mismatch, because that's a very, very big danger. What if our model is not perfect? And let's face it, it's not going to be perfect. There's always be some degree of model mismatch. And we try to make it as close as we can to the actual process. But right now, if this is my perfect match, but now I have model mismatch. So let's say here, even though our process reacts like this, we told our model reacts like that. So the model does no longer fit. And now we will be injecting false information into our controller, and then it will react to that false information, potentially destabilizing. And here is an example where I actually changed the model from 15 seconds down to 5 seconds. So that's quite a bit of difference. There's a factor of 3 difference. And not surprisingly, the most sensitive of all 3 models, the process gain, the time constant, and the dead time, the one that can cause the biggest grief is going to be the model dead time. And you can see here, it kind of obviously overshot and undershot. It did settle out. And this, again, you got to understand this is a very, very large discrepancy between the model dead time and the process dead time. If you changing the model process gain, here I went from 1 to 1.2. Surprisingly, it's a lot more forgiving. And ironically, actually, is that if you overestimate the model process gain, it kind of slows it down a little bit because the PID controller thinks that it's actually, oh my God, it's more sensitive than it actually is. But it is a lot more forgiving. And the same thing with the time constant as well. Uh, so what happens though? Let's say because we know in real life that there's the only constant of life is change. It's a very Buddhist principle. So therefore, if we know how our process is going to change, maybe we can adapt our model dynamically to keep it as accurate as we can. And we can do that if we have the right information by doing a dynamic model compensation. So let's say here, obviously, I'm injecting caustic right here, and I'm measuring that pH over here. But if I know that flow rate, if I know my flow rate through there, I know that as my flow rate increases, I know my flow rate, I know my pipe diameter. As my flow rate increases, my dead time will decrease and the converse is obviously true. So if I know my flow rate, I just do a quick calculation, I could dynamically update the model dead time. Not only that, as the flow rate increase, likely your process gain may decrease. Depends on the type of process, but it can change. And perhaps knowing, again, we would have to do some step changes, some experimentation, some bump tests to determine these changes. But as that flow increases, dynamically, I can actually reduce the model dead time. I can reduce the process gain by a certain amount. And then we could do that dynamically. And again, our attempt here is to make sure that we have as precise a model as we can have. And that kind of concludes this webinar. I know they're always kind of short and sweet, and I always wonder sometimes if they're not too quick, but feel free to ask me the questions. Again, like I said, if you have any ideas for webinars for next year, please drop me an email. I would love to hear from you. I already have some ideas. Like I said, I might recap some of my previous webinars and put in some real live examples that I've encountered, some real live data. But obviously, uh, I encourage you to reach out. You can always contact me at these coordinates, 𝗦𝗦𝗕𝗦𝗕𝗦𝗕@lakesidecontrols.com. So again, I encourage you, if you have any questions regarding the modified Smith predictor. And I know there's a 10-second time delay, so I will pause. There we go. We got our first question. So how do you actually build a model? So let me go back to here. Actually, let me go back to here. So, all right, let me go back to show you over here. Just bear with me for a second. So the question, how do you actually build a model? Essentially, you have to, again, understand your process here. And then your time constant, your process gain is just a straight multiplier. And your time constant, it could be a filter block. So most control systems have filter blocks available to them for programming. It could be a filter, could be a lead lag block where you don't use the lead, you just use the lag. And a lot of controllers also actually have a time delay block as well. Change the color to red. This is more visible. So, and I know a lot, even older DCSs actually had time delay blocks in there as well. So based on, you got the filter block for your time constant, you got your multiplier block for your process gain, and you got a time delay. That's how you build it. And obviously, once again, but you need to know your process first and try to simulate it, and that's how you build your block, your model. Now, it doesn't have to be a first order model. I've seen places where instead of a first order model, it's actually was an integrator, a level, and this was in the pulp and paper industry where you have a chip bin where you put measuring wood chips, the level, but you're injecting the amount of chips is actually on a conveyor, which can be 20, 30, 40, 50 seconds behind. And so therefore, you could build a model based on that 20, 30 seconds time delay. And instead of putting a first order process, you put in an integrated process model. So I hope that answers that question. So another question. So does Smith compensator work on nonlinear process with large set times such as pH neutralization process? And the answer is yes, because you have a lot of flexibility by being able to build it. You have a lot of flexibility in your model. And if you can characterize it properly, you can build some nonlinearities in your process model. And hopefully, again, I'm going to erase all that, build some nonlinearity in your process gain, and hopefully trying to make it as match up as close as you can to your true process nonlinearity. So the answer is yes. That was a great question. So I'm still pausing here just to see if there's any more questions. There, we got another one here. Great. Is the dead time calculated as per process estimation? Some dead time may change as such as flow rate, and you're absolutely correct. And once again, here, if I go here, hopefully if I hit the right slides, there we go. This slide right here, your process dead time will change in this example here. And so if I know that flow rate, I know my dead time is going to change based on that flow rate, and then I can calculate that dead time based on the flow rate and the pipe diameter. So what can happen here is obviously, as I said, as the flow increases, I can then dynamically compensate for that change in flow rate in my dead time model, as well as in my process gain. So that's definitely, we can actually compensate for that. So the other question is, what is the actual advantage over the modified Smith predictor over the original, the regular Smith predictor? The advantage is the fact that using a proportional only controller, model-wise, you cannot tune, or it's very difficult to tune a proportional controller process, and have it overshoot. And so it simplifies the tuning. So even if we don't have a lot of experience in tuning, because the model is a proportional model only, that we don't have to worry about the dynamics, and it makes it a lot easier to tune. So that is the advantage, is simplicity. These are great questions. And like I said, I'm not sure what kind of control systems you're all using, but I'm sure a lot of the more sophisticated ones do have dead time compensators. Some of them may be using Smith or modified Smith or more proprietary. And the common theme between any kind of dead time compensator, again, comes back to modeling your process. I do have another question here. If I want to reduce process fluctuation, should I use only PI rather than PID control when I use Smith predictor? That's a good question. There you go. D. You cannot get away from a question using D derivative. If I'm using a modified Smith predictor, I will only require a proportional and integral controller only. In fact, I may even just use an integral only controller because I already have some P in my process. So, um, no, I would not recommend PID for any kind of tuning on a modified Smith predictor. Another question: so the dead time is arranged. Does Smith predictor compensate for changes in dead time per flow rate dynamically? And the answer is yes. That if you set it up properly, what I'm just showing you right here is just the bare bones of the model itself. But we can add to our model to dynamically be updated by, in this example here, the flow rate. So we can build more sophistication into our model. As someone mentioned before, we can actually build in known nonlinearities, like a titration curve. We can build in also changes in the dead time, as well as perhaps even the model itself, as opposed to being a first order. We can make it whatever it is. Like I mentioned before, it can be an integrating a level process as well. Those are all very good questions. So in your configuration for PID, do you have a single point of access to tune the dead time accessible to operator without entering the details of the formula? The model parameters should not be available to the operator. That should be set by the control system engineer. And so therefore, and like I said, because we don't want too many cooks in the kitchen, spoils the broth. So therefore, like I said, you don't want to have too many people accessing that. So the model, again, should be only accessible by the control system engineer. So another question: what variable shall be added to the Smith predictor for changing the dead time? So right on my screen here, if I had a flow measurement right here, FT here, what I would do then is that I would put that through a characterizer block, and obviously it'd be something like this. The higher the flow, the shorter the dead time, and this would then compensate the dead time model. That's how you would do it. So once again, don't be shy. So I'll give it a few more minutes here. Give you time to type in your question and to think your question. Another question: can delta V generate model by itself? As it's programmed here, as I programmed it, the answer is no. However, if you use any of the MPC products, blocks out there, if you use any of the MPC, it will generate a model on its own. You have to use the auto tune feature where it will perturb some of the inputs for outputs, and it will generate a model on its own. And you can review also how precise, how high fidelity that model is. So yes, you can. And incidentally, I don't know if I forgot to mention, I just don't want to make this an MPC Delta V kind of commercial here, but for the MPC block, MPC Pro and MPC Plus, if you're using the single output, that single output is actually free. You do not need any special licensing. So you could build your own dead time compensator if you're a Delta V user by using MPC Plus, MPC block directly. And so the second comment, or the control system engineer has to create or generate the model, and the answer is yes. So when implementing the MSP, modified Smith predictor, yeah, should we always try to retune the PID more aggressively to speed up the process? You will have that opportunity, yes. And that's what a dead time compensator does, is that it compensates for the dead time, obviously, so then we can actually try to tune it more aggressively to be able to respond to low disturbances faster. These are all great questions. No, it is. So the question is MPC, Mary Peter Charles, MPC, Model Predictive Control Block. And there's an MPC Plus, an MPC Pro, and the the Plus block and the Pro block can have up to 40 inputs and 80 outputs. So I mean, you got to think that's a pretty complicated process. The MPC block plain old is only 8x8. The MPC Plus, I believe, is designed to handle constraints better, and the MPC Pro, if I'm not mistaken, can actually handle dynamically compensated models. It can also handle if some of the variables used actually go bad, i.e., they're disconnected. So I've used the MPC block, but I've never used MPC Plus or MPC Pro. Once again, I'm going to pause a bit here to see if there's any more questions. So another question is, can I use error squared gain PI control to offset nonlinear and little dead time process? So it's a bit off topic question, but the answer is I don't recommend that. The key, if you go back, if actually I talk about output characterization and gain scheduling in my previous webinars, we need to understand our nonlinearity before we try to undo that nonlinearity. Now, if error squared is going to do that, go ahead. But I can't say categorically that we need to do that, because we need to understand our process nonlinearity before we think about actually undoing it. So my answer is no. Once again, I'm going to pause here. And while we're here, actually, I want to thank my good friend and colleague, Patrick. He's online today. Patrick has been instrumental in helping me program and do the graphics for pretty much all my webinars. And as this being the last webinar of the year, I just want to extend a very thanks to Patrick himself. Thank you. Patrick's been very good at reading my cryptic notes and sketches that I draw out and send him out through Teams. So he's been fantastic at doing that. So another question: is there any disadvantages when using the model Smith predictor? Do you think the industry should use more often in the industry? Again, if you have a dead time dominant process, I always try to keep things as simple as possible. So if your dead time to time constant ratio is 3 or less, there's probably no real advantage in using a dead time compensator such as a modified Smith predictor. It's when your dead time starts getting longer and longer and longer, especially compared to the time constant, the dynamic response. That's where we could use a modified Smith predictor. And do I think it's underutilized? Well, you could see here how simple it is. It's actually not very complicated to implement. And so therefore, it probably is a little bit underutilized. But obviously, we need to understand PI control before we can think about the modified Smith predictor. Well, thank you. Someone just commented it was a great presentation. So thank you very much. Appreciate that. And incidentally, after this the webinar, you will have access to provide feedback. As I always say, feedback is feedback. There's no such thing as bad feedback. So once again, I'm going to pause here, see if there's any more questions. Okay, so I can see the numbers are dwindling right now. Once again, before I miss anyone here, I want to take this opportunity to wish you all safe and happy holidays. Make sure that you stay safe, and certainly wish you all the best. There's a question here about emailing the PowerPoint presentation. You will receive a recording link either later today or probably tomorrow, and you will receive a link that will show you the entire presentation. So once again, I really want to thank you very much for attending, especially some of you have attended my webinars since almost the beginning, so certainly appreciate that. And always, you know, if you have any more questions, queries, or anything like that, you're more than welcome to reach out to me, and I will certainly help you out and guide you and try to find a solution for you. Thank you very much, everyone. So I'm going to sort of call it a day for now, and we shall see you in the new year, hopefully in a different environment. Thank you very much. Have a great day.